Hi there. I wanted to look at some more examples here from lesson 2. So in this example, there's a claim that 40% of individuals like cats more than dogs. There's a survey of 80 people, and it showed that 30 of the 80 preferred cats over dogs. Test the claim that the actual proportion of people that prefer cats over dogs is less than the claim. Okay, so I'm going to go through the 4-step process. First step, hypotheses. Null hypothesis, it's a proportion, and the claim is 40%. Alternative hypothesis, it says less than, so we will test for less than. The alternative hypothesis gives me the direction. So this is telling you when the time comes to shade, this is going to be a left-tailed test. Second step is the model. I actually have a bunch of options when it comes to the models. I could use binomials, I could use normal approximation for binomials, but one of the most common one for proportions is this p-hat model. P-hat is normally distributed with the center of p and the standard deviation of the square root of pq over m. P-hat is the name of the model, n stands for normal, and p is coming from the claim, 0.4. If your P is 40%, then your Q is 1 minus, that's 60%. And this is for a sample of 80 people. I'm going to type that standard deviation into my calculator and see what we get. We've got the square root of 0.4, 40%, 0.6, 60% over 80. And this gives me 0.055 if I round a little bit. I should check assumptions. I just kind of want to go through these calculations with you instead. Third step is to calculate the p-value. And the p-value is the likelihood of our sample data or more extreme. And our sample data success rate was 30 out of 80. So I'm looking for that much, and the symbol here is coming from the alternative or less. I'm going to type that 30 out of 80 into a calculator to see what I get for my sample data. And when I do so, I got 0.375 or 37.5%. So if I'm drawing a picture for what's going on here, in the center of the curve, you're always going to have the claim. That claim is going to come from the null hypothesis. In this case, the claimed value is 40%. If you were marking this thing, you would count by 5% or so. So this would be roughly pretty close to 6%. So this would be roughly 34%. This would be roughly 46%. And my sample data is 37.5. 37.5 is fairly close to the center. So P is the claim, P hat is my data, and that's where I start to shade. Now I can shade this to the left, I can shade this to the right, or I can shade this as two tails. And the spot that I know to shade from is based off of this alternative hypothesis. This is telling me less, so I'm going to shade this thing to the left. So I'm going to find my test statistic or my z-score. And the way I'm going to find my z-score here is I'm going to take the value that I care about from the sample data. I'm going to subtract the claim from the center, so the data value minus that claim or null hypothesis center, divided by the standard deviation. So in this case, my value of interest is at 37.5. The claimed value in the center is 40%. and the standard deviation is 0.055. I'm going to type this into a calculator to see what I get. And I've got parentheses around the top here, 37.5 minus 40% divided by 0.055. I could actually copy and paste that standard deviation to get something even more accurate. I get negative 0.45 for my z-score. To get my p-value from here, since this thing is shaded to the left, that's going to be the value inside of the table. I'm also going to show you how to do this with some technology here. But it's shaded to the left, so that's my table value. Negative 0.4 meets the 5, and that happens at 0.3264. And that's a pretty large p-value, especially compared to what is considered a neutral alpha level of 5%. So my p-value is greater than or equal to my alpha significance level of 5%. And since it's bigger than alpha, this means I would fail to reject the null hypothesis, which means I do not have evidence of the alternative. So I do not have evidence that less than 40% of people prefer cats over dogs. I like both cats and dogs. Okay, I want to show you how you can look up that z-score using technology like GeoGebra. And I also want to share with you a formula that I've seen sometimes for this z-score. So if you wanted to get this z-score in a slightly different method, you could use the equation p hat minus the claim p, so that's the sample data, minus the claim p, divided by the square root of pq over n. Now, if you were to do this, you would see that you get the same values as you had for your model over here. So it's not really a different formula as much as it's just taking this and it's writing it as a single step. So when you're looking at this model, the thing that you're subtracting is your center. And that's the same center as you have over here. When you are looking at the bottom, that square root number is going to be your standard deviation. And that remains your standard deviation over here. So if you like using that formula for finding the z-score, go for it. It's equivalent to the same method that we got going on for using the model and then calculating the z-score. Okay, now if I wanted to look this z-score up in GeoGebra, I could. I'm going into geogebra.org/classic. I like the classic version. Kind of like Coca-Cola Classic. And then I'm going to choose the option for probability. And that should be on that side menu there when you first open it. That's a perspective probability. And it looks something like this. I'm going to leave mu as 0. I'm going to leave sigma as 1. And if I click these buttons, it changes the directions it's shaded. So I've got the option for a left-tailed test if I choose this option on the left. I've got a right-tailed option on the right. And this option where the parentheses are sort of brackets are opening outwards, that's actually a two-tailed test. And I can look at the size of both those tails together. So a great way to look up that p-value. In this case, I have a left-tailed test. And my z-score, which I'm going to type into this lower block here, is negative 0.45. And this gives me a p-value of 0.3264. I'm getting the same thing. So if you like using GeoGebra to calculate that p-value, go for it. Again, you go into GeoGebra, you open up probability. Inside of normal, make sure it's shaded to the correct direction. You type the z-score into the block, and it spits out your p-value. There are some instructions for how to do this in the TI 83, 84, and 89. I also want to show you how to do this in GeoGebra because there are some videos for this up online already. So inside of GeoGebra, when you go into probability, there's an option for statistics. And the name of the thing that we're doing right now is we're using z-scores and we're doing a test. So estimates are confidence intervals, test are hypothesis test. And we are looking at not means, but proportion. So z test of a proportion. If you wanted to do a confidence interval, that would be a z estimate of a proportion. And it asked me for the null hypothesis value. That was 40% for this problem. I wanted this thing shaded to the left. I had an alternative hypothesis of less than. I have a sample success rate of 30 out of 80. When I do this, it gives me my z-score. This is sometimes called your test statistic. And that's a z of negative 0.45 or negative 0.46, depending on how you round there. And your p-value, 0.32. So GeoGebra is a really great way to double check my work to make sure I'm on the right track. When I did this, I got a test statistic or a z-score of negative 0.46, just rounded a little bit different for my standard deviation. So I have a little bit of round off there. And a p-value of 0.324. Looking pretty good. Let's try another one of these out, and let's use GeoGebra afterwards with this z-test of proportion, see how close we are. Okay. So let's look at a problem that was in an earlier video involving SUVs. So suppose that there's a claim that 33% of all vehicles or cars sold in the US are SUVs. And after some investigation, it appears that the actual value is different than claimed. There's a sample of 500 recently sold cars, and it shows that 145 of those are SUVs. So the claimed proportion, the null hypothesis, is 33%. And we think it's actually different. Whenever you're testing for a difference, this is going to be a two-tailed test. Two-tailed test will have a positive and a negative z-score, always. So my picture will look something like this. Second step is the model. I'm working with the normal distribution. I'm using the value p square root pq over n. P is the p from the claim, 33%. So that becomes my center. If my p is 33, then my q is 67. They add up to 100. They're complements. And this was for a sample of 500. I'm going to type that in to see what I get for my standard deviation. I've got square root 0.33 times 0.67 divided by 500. And if a problem ever asks for a model, it wants to know, is it normal, a t-distribution, or something different? Like, what type of model are you using? What is the center of the average, 33% in this case? And what's the standard deviation? So it's looking for the name of the model, the center, and the standard deviation. Third step is my p-value step. And I am looking at the likelihood of my sample success rate. And I had 145 successes out of 500 trials. And I'm testing for difference. I'm looking at a two-tailed test. That 145 out of 500 is 29%. So on my curve, I'm going to have 33% in the center. That's my claim. And my data is going to be at 29%. So I need to find my z-score and look it up. So z, I'm going to take my value of interest. So my value is always going to be coming from my sample data. I'm going to subtract my center of my model, and I'm going to divide by the standard deviation. So my sample success rate was 29%. The center of my model was 33. My standard deviation was 0.021. I'm going to type this into a calculator and see what I get. And I wrote that with that formula with all those symbols in one spot, just in case you like using that formula. And I got a z-score of negative 1.90. Now this is a two-tailed test, so this has a negative z-score of 1.90, and it's going to have a positive z-score of the same thing but positive 1.90. Now I'm going to look this up inside of my table. And I'm going to look at that left tail. That's going to be that negative z-score. And I'm going to find negative 1.90. And when I do so, I got 0.0287. Again, to find that, I went to the negative 1.9 row and the 0 column, negative 1.90. That gave me 0.0287. When I multiply that by 2, I get a p-value of 0.0574. If I'm using an alpha level of 5%, this p-value is bigger than 5%. Bigger or equal. And whenever it's bigger or equal, that means you're going to fail to reject the null hypothesis. And if you're failing to reject, that means you do not have evidence. So in this case, we do not have evidence that the proportion of SUVs is different than 33%. I want to use technology to double check my z-score and my p-value there. And I'm still in the same z test of a proportion. Null hypothesis value 33. My sample data here, I had 145 successes out of 500 trials. It gives me a z-score of negative, and I got to check my symbol. This would be if it was a left-tailed test. Do you notice how that left-tailed test is just giving me one of those areas? So when I do two tails, it makes that twice as big. So it gives me that same z-score, negative 1.90. That's looking great. And when I multiplied it by 2, I ended up getting a p-value of 0.057. I could also use GeoGebra, probability, and the curve to look it up on the curve. So two tails shading out. My lower tail is negative 1.90. My upper tail, positive 1.90. Both of the tails are the same size, that 0.0287 number. When I multiply this by 2, because I have 2 of them, I get this p-value of 0.0574. Let's try another one. I like these. I like being able to test claims. I think that's a neat thing that statistics is able to do. Census.gov claims that 29.7% of students work full-time. An informal survey of PCC students shows that 18 out of 68 worked full-time. Tests the claim that the actual proportion is higher than claimed. All right, first step. I'm working with proportions. The claim is 29.7%. Alternative hypothesis. We are testing if it's more than that. If we're testing for more, this is going to be a shade right situation. And when we're using our table, that's going to be a 1 minus thing. Our model is going to be based off of this null hypothesis value. And I'm going to plug that in for our P. I'm going to plug that in for our P again. And our Q is going to be 1 minus or complements. So if I do 1 minus 0.297, that gives me 0.703. 70.3% and 29.7% add up to 100%. And the number of trials I have here, 68. I'm using the normal model. I have a center of 0.297. I'm going to type in that standard deviation. And I end up getting a standard deviation of 0.055. So I'm going to move to that third step, that p-value step. And the p-value is going to be looking at the likelihood of our sample data. Our sample data here was 18 successes out of 68 trials. And the direction I'm shading is from that alternative hypothesis. I'm testing for higher. 18 out of 68. As a decimal, that's 0.2647 or so. 0.265 if I want to match the same number of digits. When I'm drawing my picture, I'm going to have the center of 0.297, and my data is showing up here at 0.2647. And I'm testing for that amount or more. I can already tell this is going to be a really large p-value because over half the curve is shaded in. The p-value is the size of the shaded in region. I'm going to find my z-score, my test statistic, by taking my value. My value comes from the sample, 0.2647. Subtract the claim. The claim is the center of your model, 0.297. Divided by the standard deviation of 0.055. I'm going to type this into my calculator and see what I get. And then I got, up to a little bit of rounding, the z-score of negative 0.59. If I look that up inside of my normal table, I'm going to go to the negative 0.5 row and the 9 column and see where they meet up. And negative 0.5 meets the 9 way down here at the end at a table value of 0.2776. Since this is shaded to the right, I would want 1 minus this. So my p-value is going to give me 0.7224 or so. That's a massive p-value compared to pretty much any alpha level that you can choose. For example, compared to 5%. And that's way, way bigger than that. And since it's bigger, we fail to reject that null hypothesis. And when we fail to reject the null hypothesis, that means we don't have evidence of something. In this case, we don't have evidence that more than 29.7% of students, PCC students, work full-time. Let's check these numbers in GeoGebra. So checking just the z-score to get the p-value, I'm in my calculator here, shaded to the right. I'm going to type in my z-score. My z-score is negative 0.59. And this gives me exactly the same p-value, 0.7224. If I want to check the whole test, I'm looking at z-test of a proportion. The claim is 29.7%. There have been 18 successes out of 68 trials. I am testing for more. I think it's higher than claimed. So I'm choosing the more symbol. And when I do so, this gives me a z-score up to a little bit of rounding of negative 0.58. That's looking pretty good. And it's giving me a p-value of 0.72. That's the same p-value I got. So GeoGebra is a really fast and easy way to double check my work to make sure I'm on the right track. Let's check out more. So in this next problem, we have US News claims that 86.6% of Oregonians have health care. And we want to test if the actual proportion is different than claimed. So an informal student survey showed that 64 out of 68 students had health care. And it said test the claim. Now, I'm seeing this 64 out of 68, and I'm a little bit worried about my assumption check. So as a reminder, you need to pass 3 assumptions in order to do the calculations. We didn't calculate these or check these on the last ones, but I do want to check it on this one. Those assumptions that need to be met in order to be able to do that calculation, the 4-step process, are random, an independent sample or sampling less than 10% of the population, 10% rule, and a large N. So the informal survey, I'm not entirely sure how these students were selected. So for random, I'm not sure. PCC has around 27,000 students. It's a really big school. So 68 is less than 10% of students. That looks great. So I'm not sure about the first one. That's not a complete deal breaker, although I should be aware of it. Second one looks good. large N, I'm going to check N times P, and I'm going to check N times Q. And both of these should be bigger than or equal to 10. I need to have at least 10 expected successes and at least 10 expected failures. N times P, I have 68 samples. And my success rate, my P, the claim is 86.6%. So when I do N, 68, times P, I get 58.888. This is looking great. So I don't know why I was so concerned. So far, everything seems to be fine. And if it is, I'll go through the 4 steps here. Let's check N times Q. My N is still 68. My Q is the complement. So if you think 100%, take away 86.6. 100, take away 86.6. This gives me a Q of 13.4%. If I do 68 times 0.134, I get 9.112. That's less than 10. I need to have this number be 10 or bigger. When you fail an assumption, you should not continue to do the analysis. So in this case, because my assumptions are not met, it is not a large N, we do not proceed with this 4-step process. Now, on homework, you might be asked to go through those steps to still find the z-score and the p-value, to practice finding the z-score and the p-value. But in practice, when you find that your assumptions are not met, you should not continue doing the analysis. So for this next one, I might be a little bit concerned about this 250 trials and a 20% success rate. So preemptive, I'm just going to check large N. N times P, 50. And if P is 20%, then Q is 80%. Yeah, this is looking nice and large. So this one's not going to have that same problem where it's less than 10. I'm feeling good about example D here. It's estimated that 20% of all freshwater fish in the US have high levels of mercury. So for my 4-step process, the claimed value proportion is 20%. And it says, suppose a fish market has 250 fish that are tested, so an N of 250. And I have a success rate of 60 out of 250. Tested claim that the true proportion is different than claimed. So different means does not equal. So this is going to be a 2-tailed test. I'm going to find my model. P hat is normally distributed with a center of P and a standard deviation of root PQ over N. My claim is 20%. The model is always based off that null hypothesis claim. And if P is 20%, then Q is 80%. And the number of samples here is 250. So this gives me a center for an average of 20% for this model. And for that standard deviation, I have the square root of 20 times 80% over 250, 0.025 or so. Third step is that p-value step. And the p-value is the likelihood of my sample success rate. Sample success rate here is at 60 out of 250, or more extreme. I'm testing for a difference. It's going to be a two-tailed test. I'm going to type that 60 out of 250 into my calculator to see what I have for my sample data. And when I do so, I get 0.24. So if I'm drawing my picture out, in the center of my curve, I have a 20% success rate. And I'm counting by about 2.5%. So 2 standard deviations up is 25, 2 standard deviations down is 15. And I have a value of 24. So I'm going to shade from 24 up. And two tails, I'm going to have a shadow one on the other side. And that much and down. I'm going to find my z-score by taking the value from my sample, my p-hat. Subtract the center from p, 20. Divided by the standard deviation, the square root of pq over n number. That's the 0.025. And I'm going to type this into a calculator and I'll see what I get. 0.24 minus 0.20 divided by, and I could always type up on my calculator, this is true of most calculators, and hit enter to just copy and paste that, or I could type in 0.025. This gives me a z-score of 1.58. But a reminder, this is a two-tailed test, so that other z-score is the same thing, but negative. So we're going to go inside of our table, and our p-value is going to be 2 times that left tail. And I'm going to look up negative 1.58. So that's going to be in the negative 1.5 row and in the 8 column. And that gives me 0.0571. When I multiply this by 2, this gives me a p-value of 11.42%. That's a pretty large p-value. So for the conclusion, your p-value is bigger than an alpha of 5%. And if it's bigger or equal, that's when we fail to reject. And if we fail to reject the null hypothesis, that means we do not have evidence. So we do not have evidence. ... We do not have evidence that the proportion of seafood that has dangerously high levels of mercury is different than 20%. I want to double check this using GeoGebra. So I'm in z-test for proportion. I have a claim of 20%. I have a success rate of 60 out of 250. And that gave me the size of just one tail there. So I have to make sure I'm choosing that does not equal symbol. It should be 2 tails. Gives me my matching z-score. That's a great sign. And it gives me 11.4%. 11.4%. I'm getting the same p-value. You can also use the probability option to look at the size of the 2 tails from negative 1.58 and down, and positive 1.58 and up. That shows you each of those tails is 0.0571, and in total your p-value is 0.1141. That's what we got. Finally, this last question asks you to create a 90% confidence interval. And if you use the confidence interval formula, since we failed to reject the null hypothesis, you're probably going to see that null hypothesis of 20% show up in your model. My formula is p hat plus or minus z star square root p hat q hat over n. My sample success rate is 24%. My z star, my critical value, is 1.645. Sample success rate of 24%. Gotta be really careful with that, 24%. Sample failure rate of 76%. And this is for 250 samples. I'm going to type this into my calculator once with the minus and once with the plus to get a low value and a high value. And let's see what that looks like. And then I'm going to show you how to check this in GeoGebra. But I have p hat plus or minus z star square root p hat q hat over n. And it's based off of my samples. So I have 24% minus 1.645 square root 2476 over 250. So on the low end, the actual proportion that have a dangerous high amount of mercury could be somewhere between 19.6%, that's what I have for the low, and doing it with a plus, 28.4% with 90% confidence. So I would say I'm 90% confident that between 19.6 and 28.4% of fish has a dangerously high level of mercury. If I want to check that inside of GeoGebra, inside of your probability calculator for statistics, instead of doing a test, you would be doing an estimate. Confidence level. And you may notice it automatically assumes that you want to do these things together. So it dropped in the 60 and 250 for me. Nice. That is my sample success rate. My confidence level should be 90%. Let's check some things out. It gives me an interval of 24% plus or minus. If I type this margin of error into my calculator, I have a margin of error of 0.044. This gave me a low value of 19.6% and a high value of 28.4%. Estimates are used for intervals. Tests are used for hypothesis tests. So that took a look at some additional problems to practice involving hypothesis test, and I hope that you found that useful. As always, I'm available for questions as things come up.